Hello and welcome to Control Systems lecture. We will start with a new topic called the time response analysis. This is found in chapter 4 of your textbook. At the end of this lecture, you will be able to use poles and zeros of a transfer function to determine the time response of a control system and then describe the transient response of first order systems. In the next class, we'll look at second order systems. So let's look at poles, zeros, and system response. If you have a transfer function given as g of s equals to n of s over d of s, where this is the numerator polynomial and this is the denominator polynomial, your zeros are the values of s that causes the transfer function to become 0. In other words, the roots of this equation are referred to as zeros. And then the roots of the denominator, the equation of the denominator or the polynomial of the denominator are referred to as poles, because any roots here will give d of s to be 0 and this will become infinite. And then for a system, the order of the system is the order of the polynomial d of s. This is a first order system, and I would like to explain it this way. So you have the block diagram of the first order system. You have your input r of s, which is a step response, and then you have your g of s. The force response is generated by the pole of the input. So you see the input is 1 over s, which means that you have a pole, and this pole will be where at the origin s equals to 0. We use x to represent poles and we use zeros to represent zeros. So you see the input pole will be x at the input or the origin. Then the pole of the transfer function generates the shape of the natural response. This is now the natural response of the system, and we have this is now our s plus 5, which means that minus 5 will be our pole. And you know that minus 5 will give us, if we do the Laplace transform and we find the time response, it will give us e raised to power minus 5t, which is an exponential system. So this part of the equation is your natural response of the system, which is generated by the transfer function denominator. And here the input generates the force response. Now let's look at the effect of A on the real axis. So this is the real axis, this is the imaginary axis, and this whole plane is called the S-plane. So a pole at minus A here generate response k e raised to power minus alpha t. So you can see that a pole on the real axis generates an exponential response of the form e raised to power minus alpha t, where alpha is the pole location on the real axis. The larger the alpha to the negative side, the faster the exponential transient response dies out. Because if you have a minus alpha, if alpha is large, you will find out that the exponential system will not will die off very quickly, so it will just go up and die off very quickly. So the larger the alpha, the more stable your system, or in other words, the further away your pole is from the imaginary axis, the more stable your system will be. So we can write the time response of the system shown by inspection. So this is a system shown just for us to be able to have an idea of how this system is going to respond. Here we have the input, which means we're going to have a pole at origin, and this is the transfer function, which will give us the shape of the system. So if you look at this, you can quickly write that c of s is k1 over s plus k2 over s plus 2 plus k3 over, so you perform partial fraction expansion here, plus k4 s plus 5. Here now the next is, you can, of course we know we have to find k1, k2, k3, k4, but you can also write the time response directly to give you k1 plus k2 e raised to power minus 2t plus k3 e raised to power minus 4t plus k4 e raised to power minus 5t. So this will be the form of the response of the system that we have in this block diagram. Just by inspection, we can compute this. So where the first term is the force response, which is coming from the input, and the rest of the response make up the natural response of the system. So first order system with a zero, when we say, without a zero, it means that there is no any root in the numerator, and so you have one root at the denominator, which will be s equals to minus a, and you can put that as a pole because we said this is a pole, so we have it here as a pole. If the input is a unit step, if now we have a unit step input to this first order system without a zero, the Laplace transform of the system will give us a over s plus a, and we can take the inverse Laplace transform of this system, and this will give us the force input, which is the due to r of s, plus the natural response, which will give us e raised to minus a t. So if you plot this first order system by choosing different values of time and plotting ct, so you have ct on this axis and you have your time on this axis, you will have this shape of the response, and you can see the blue line here is your response and is exponential. When t, or when the time is 1 over a, what do we have? When time is 1 over a, you put in here t equals to 1 over a, so this cancels out. You will be left with 1 minus e raised to minus 1, which is equals to 1 minus, this is 0.37, and this gives you 0.63. What does this mean? It means that when the time is 1 over a, your system response will have achieved 63% of its final value. That's what it means. And we will soon see that this is referred to as the time constant for a first order system. So let's put together now the transient response performance specifications for a first order system. We've already discussed the time constant. I explain it here briefly again. The time constant is found at time equals to 1 over a, and it gives us a final response of the system of 0.63, or we can say it is the time it takes for the step response to rise to 63% of its final value. So if it's a unit step, it will achieve 0.63. You can imagine if it's, for example, not a unit step, let's say it's 5 over s, then you find 63% of 5, and that will give you your time constant. So here we have it right again, showing you the time constant achieving 63%, system achieving 63% of its time constant. Then the next specification is called the rise time, and it is the time it takes for the waveform to go from 0.1 to 0.9 of its final value. I must say that this is not cast in concrete because this depends on a certain specification. Some companies may decide that the rise time should be measured from 0.2 to 0.9. But in this course, we'll be using 0.1 to 0.9 because this is commonly used. In this case, we'll find out what is CT at 0.9 and what is CT at 0.1, and then we subtract the two to find what our rise time will be. So first of all, C of t at 0.9. So if C of t is 0.9, you substitute it into this equation. 0.9 is equals to 1 minus e raised to minus at, and here you just say e raised to minus t is equals to 1 minus 0.9. That gives you 0.1. you take the natural log of both sides, and this gives you minus AT is equals to natural log 0.1. And from here you can find that your T is equals to natural log 0.1 over A, which will give you 2.31 over A. You do the same for when CT is equals to 0.1, and you will get T equals to 0.11 over A. And from there we can say then that T is equals to 2.31 over A minus 0.11 over A, which will give us 2.2 over A. And this is referred to as your rise time. So your rise time can be computed as 2.2 over A. Then the next specification is settling time. So C of T, again, this is our first order equation. The settling time is the time for the response to reach and settle within 2% of its final value. Again, this specification can be specified differently for different companies. For us, we will use the 2%, which is used in most textbooks, and this is a fairly good specification to use 2%. Therefore, we're going to now say C of T is 0.98 because we said it is the time for the response to reach and settle within 2%, which means the system will have achieved 98% of its final value. So in that case, C of T will be 0.98. So we substitute 0.98 into this equation, and then we find our T. And here we find that our T is equals to 4 over A, which is our time response. So our, which is our settling time. So our settling time is equals to 4 over A. And you can see it's right here, 4 over A, when the system have settled down. So this is when the system have settled. So it's 4 over A. So let's look at the first order transfer function estimation. What we mean here is consider this first order system. So you have this first order system, and you want to use other means to estimate the system. You know, at times we have systems and we don't have a mathematical equation for the system. How do we estimate their transfer function? So this is a generic form of the first order system. If we excite this system with a step input, which is 1 over S, our output then will be K over S plus AS. So the step response will then be K over AS minus K over AS plus A. Of course, this is after you've performed your partial fraction expansion. If we can find the values of K and A from experiment using step input, we can obtain our transfer function of the system, which means we can estimate the transfer function. So the generic transfer function we know is K over S plus A. So if by some kind of experiment we can find our K and A, we should be able to estimate the transfer function of a first order system. So now let's look at this. So you have a black box. So it's a system, and you don't know what is inside this black box. So you excite it with a step response. So you put in a signal, which is a step response, and then you measure the output, which is your C of S. And you can plot this output using some software, computer software. You get the output, and this is your output. Now, how do we find the transfer function of this output based on this system? Well, we know a few things. For example, we know that we can measure the time constant from this system, from this plot. How do we measure the time constant? We note that the final value of the amplitude for this system is 0.72. And we know that time constant T is reached at 63% of the final value. So final value is 0.72. Therefore, our time constant will be at 0.63 times 0.72, which is 63% of 0.72, which is 0.45. So we come here and we find our 0.45 to the graph, and then we measure the time. And here the time will be 0.13, which means that our time constant, tau, is 0.13 seconds. So we know that tau is 1 over A, which is equals to 0.13. We have measured this, and we now say that therefore A is equals to 1 over 0.13, which is 7.7. Next, we want to find K because we said the first order system is K over S plus A. So now we want to find K. Note that the system reached a steady state value of K over A at 0.72. So at steady value 0.72. So we now know that our K will be equals to 0.72 multiplied by A, which is 7.7. And therefore our K is 5.54. Now we have K and we have A, so we can write our transfer function, which will be 5.54 over S plus 7.7. So from a black box, we're able to estimate our system, which means that if you have the plot based on a unit step function, you can use the graph to estimate your system. Now we're going to look at a skill assessment exercise, which is 4.2 in your textbook. The question is that a system has a transfer function g of s 50 over s plus 50. The question is to find the time constant tau, settling time t of s, and the rise time t of r. So we already have the equations of these various constants or specifications. So let's look at the solution. First, write the system in the generic form g of s is equals to k over s plus a. You are interested in finding a. Once you know a, problem is solved. In this case, you can see that if you put this in this form, that our a is equals to 50. Therefore, our time constant is 1 over a, which is equals to 1 over 50. That gives you 0.02 seconds. And then our settling time, which is t of s, is 4 over a. That gives us 4 over 50. So we have 0.08 seconds. And then our rise time is t of r is 2.2 over a, which is 2.2 over 50, which is equals to 0.044 seconds. So you can see that a plays a very crucial role in the specification of a first order system. Once you can find your a, you can give the specification of your system. In case you are doing a design, you can then manipulate whatever variables affect your a in order to achieve a certain rise time or a certain settling time or a certain time constant. In the previous lecture, we discussed the first order system and introduced the concept of poles, zeros, and their plot on the S-plane. We also introduced and defined the transient response performance specifications for this class of systems and developed their equations. That is, the specifications which we discussed are the time constant, the rise time, and the settling time. We will now extend the concept of poles and zeros and the transient response to second order systems. We observe that changes in the first order system parameters will only change the response speed of the system. However, changes in the parameters of a second order system will change the form of the response. Second order systems could exhibit a damp or pure oscillation for its transient response. The block diagram in figure A is a general form of a second order system with two poles and no zero. Using this generalized system, we will show how changes in the parameter A and B yields different responses of the system. Note that changes in the numerator only have a scaling effect and will not affect the form of the derived result. Also note that we are using a step response as our test signal, so it gives us an idea of the response that we expect being a step response. In carrying out this demonstration, we will not go through the rigor of partial fraction expansion and inverse Laplace transform. In the first case, let's take A equals to B, which is equals to 9, Note that in all cases, the input signal, which is a unit step function, yields a pole at the origin that provides the constant force response. The two poles of the system generate the natural response. For this case, therefore, the poles will be S equals to minus 7.854 and minus 1.146, which are two distinct poles on the real axis, and their exponential frequency will be equal to the pole location. We can easily write the response as C of t equals to K1 plus K2 e raised to power minus 7.854 t plus K3 e raised to power minus 1.146 t. This response is called overdamp. Now let's change A and make it equals to 2 while keeping our B same as 9. This will give us two poles which generate the natural response of the system, and these poles are located at S equals to 1 plus or minus j square root of 8. The transient response is made up of an exponentially decaying amplitude generated by the real part of the system poles times the sinusoidal waveform generated by the imaginary part of the system pole. The time constant of the exponential decay is equal to the reciprocal of the real part of the system pole. This can be further depicted graphically like this, where the value of the imaginary part is the actual frequency of the sinusoid. It is called the damp frequency of oscillation, or omega subscript d. The steady-state response is generated by the unit step input, which is the pole located at the origin. This type of response is called on-the-damp response. In the next case, let us change A and make it equals to 0 while keeping B equals to 9. This system will produce two imaginary poles at plus or minus J3. These generate a sinusoidal whose frequency is equal to the location of the imaginary poles. The output can be estimated as C of t equals to K1 plus K4 cos 3t minus phi. This response is referred to as undamped because it does not have a real part, which implies it does not have any damping. If we now let A equals to 6 while keeping our B equals to 9, we will have the case of repeated roots. This will give us two poles on the real axis at minus 3 that will generate the natural response of the system. This response is an exponential, and an exponential multiplied by time. This type of system is called critically damped. These are the fastest possible response without an overshoot. This figure shows the response of all four cases of different values of A that we can achieve. So one, we can achieve an undamped with two poles on the imaginary axis, or two, on the damped with two complex conjugate poles, 3, critically damped with repeated roots on the real axis, and 4, overdamped response with two poles on the real axis. Now that we have an idea of how changes in the second order parameters affect the response and shape of the system, behavior, let us define these parameters and relate them to the second order transient response specifications. This equation represents a second order system in a generalized form, and we will use this to develop quantitative specifications. We will start by defining two physical quantities of the second order system, these quantities will be used to describe the characteristic of the second order transient response, just as we did with the time constant for the first order system. The two physical quantities are the natural frequency omega subscript n, which is the frequency of a second order system without damping, and then the damping ratio zeta, which is the measure of the rapidity or the fastness with which a second order system will respond to any input signal, for example, a step function, when we assume that all the system parameters remain constant. It is the ratio of the exponential decay frequency to the natural frequency. Let us demonstrate how to find zeta and omega n from a second order equation. If you are given the transfer function g of s is equals to 36 over s squared plus 4.2s plus 36, and you are asked to find its natural frequency and its damping ratio, you will have to compare terms between the given transfer function with the generalized second order system form. You can see that then that omega n squared is equals to 36, and therefore we can find our omega n to be the square root of 36, which is 6. And then 2 zeta omega subscript n will be equals to 4.2, and hence our zeta is 0.35. Now let us relate the two physical quantities, that is the frequency, the natural frequency omega subscript n and the damping ratio zeta, to the poles of the system. From the generalized second order system, using the quadratic equation, we can find the solutions of the equation or the roots of this equation as s1 and 2, that is the two roots, equals to minus zeta omega subscript n plus or minus omega subscript n square root of zeta square minus 1. We can see that the response of the second order system is a function of zeta. So for zeta equals to 0, we have a case of undamped system. For zeta lying between 0 and 1, that is zeta greater than 0 but less than 1, we have the case of undamped system. And then for zeta equals to 1, we have the case of critically damped. And for the case of zeta greater than 1, we have the case of overdamped. Let us now see how these are plotted on the S-plane. Observe the position of the poles and their impact on the system's response. Most physical systems fall within the underdamped category, and we'll look at this system in detail in our next lecture. Welcome to Control Systems Lectures. We will now continue with our lecture on time response analysis, which is found in chapter 4 of your textbook. The underdamped second order system is one of the common models for physical systems, and hence it warrants a proper description for the purpose of analysis and design. Apart from the natural frequency omega subscript n and damping ratio zeta specifications, there are other peculiar specifications to this system that we need to consider. Our first goal is to define these transient response specifications. We will start by finding the step response for the generic second order system shown by equation 1, and then we will find the transform form assuming that zeta is less than 1. This implies that we are dealing with a complex conjugate solution case. Performing partial fraction expansion on equation 2 for the case of complex conjugate will yield equation 3. Taking the inverse Laplace transform of equation 3 will yield equation 4, where Phi is tan inverse zeta over the square root of 1 minus zeta squared. When we plot equation 4 for different values of damping ratio zeta, we will get this figure. Note how the oscillation increases when the value of zeta is lower. In this plot, the x-axis is the normalized time using the natural frequency as a normalizing factor. It means that the natural frequency is only a scaling factor and will not affect the response in any other way than to scale it in time. Apart from the natural frequency and damping coefficient, we would like to introduce other specifications for the underdamped second order system. These are the rise time, which is the time required for the waveform to go from 0.1 to 0.9 of its final value. Then we have the peak time, which is the time it requires for the system's response to reach its first or maximum peak. And then we have percentage overshoot, which is the amount the waveform overshoots the steady state value. And then settling time, the time required for the transient's damp oscillation to reach and stay within plus or minus 2% of the steady state value. All these specifications will be evaluated as functions of the natural frequency omega subscript n and damping ratio zeta. Note that it is not possible to obtain a precise analytical expression for the rise time, and hence a curve fitting method is employed. We define the peak time T subscript P as the time required to reach the first or maximum peak, starting from the response equation of a general second order system. We can find T subscript P by differentiating C in the time domain Ct, that is the response of the system, and equating it to 0. This will yield equation 5. For this equation to be 0, it means that the sign quantity must be 0, and this will occur when omega subscript n square root of 1 minus zeta squared t is equals to 0 or pi or 2 pi, because any of these quantity will give us sign of this quantity to be 0. Hence we can write t as shown in equation 6. So we now have the equation with respect to the time t. Each value of n in this equation will yield a maxima or minima. At n equals to 0, we get the first point on the curve with 0 slope. And then at n equals to 1, we have our first peak, which is T subscript P, which is then given by equation 7. We define the percentage overshoot as the amount that the waveform overshoots the steady state or final value at the peak time, expressed as the percentage of the steady state value. From the graph, we can see that it can be expressed by C max or C subscript max minus C final divided by C final multiplied by 100, which is equation 8. C max is C of t at the peak time, Tp, which yields equation 9. For the unit step input, C final will have to be 1. Hence, if we substitute equation 9 and 10 into 8, we will get the expression for the percentage overshoot shown in equation 11. From equation 11, it shows that if we know the percentage overshoot, we can easily compute the value of zeta. So from 11, we can make zeta the subject of the formula, which will yield equation 12. You can verify this for yourself. From the definition of settling time, it means we need to find the time it takes the amplitude of the decaying sinusoid in equation 4 to reach 0.02. Therefore, we equate the amplitude to 0.02. Note that this is conservative because we are assuming that the cos component is 1 at the settling time. Hence, settling time will be given by equation 14. The value of the numerator of equation 14, log minus log 0.2 square root 1 minus zeta square, for values of zeta greater than or equals to 0 and zeta less than or equals to 0.9 yields values between 3.91 to 4.74. You can verify these by substituting the values of zeta in this range into this equation, and you'll get that for each of these you will get value between 3.91 to 4.74. Therefore, we approximate the numerator to be 4. Hence, we can write our settling time t subscript s to be equals to 4 over zeta omega subscript n. Now, let's look at the rise time. We define the rise time as the time required for the waveform to go from 0.1 to 0.9 of the final value. There is no precise relationship between rise time and the damping ratio. A curve fitting technique, however, is used. The curve is produced using equation 4 and the varying values of zeta. The time axis is normalized with the natural frequency. This curve can be approximated by the following polynomials. Maximum error is less than 0.5% for zeta values of lying between 0 and 0.9. And the second polynomial gives a maximum error of less than 5% for zeta lying between 0.1 and 0.9. That is, zeta is greater than 0.1 but less than 0.9. In this example, we are to find the peak time, the percentage overshoot, and the settling time, and the rise time from transfer function given this particular transfer function. Try solving these using all the equations we have derived, and you should get the following solutions. We will now relate the second order system specifications to the poles locations. Recall that we use the generalized second order system given by G of S to find the poles, which are the two poles S1, 2 equals to minus zeta omega subscript n plus or minus omega subscript n square root of zeta square minus 1 for zeta greater than 0 and less than 1. We now plot these poles on the S-plane, where omega subscript d is referred to as the damp frequency of oscillation, and zeta subscript d is the magnitude of the real part and is called the exponential damping frequency. Using Pythagorean theorem, we can see that the radial distance from the origin to the pole is the natural frequency omega subscript n. And the cosine of the angle theta, cos theta, is the damping coefficient. Let us relate the specifications to the poles. The peak time is given by equation 7 from the plot. This is pi divided by the imaginary component, where omega d, the damp frequency of oscillation. The settling time is given by equation 15, and it is 4 over the exponentially damping frequency, which is 4 divided by the real part. Equation 7 shows that the peak time is inversely proportional to the imaginary part of the pole. Therefore, horizontal lines are lines of constant peak time. Similarly, equation 15 shows that the settling time is inversely proportional to the real part of the pole. Since zeta is cos theta, Radial lines are lines of constant zeta. And since percentage overshoot is a function of only zeta, it means that radial lines are lines of constant percentage overshoot. We will now use a step response to show how moving the poles influence the system. In figure A, we move the poles in the vertical direction while keeping the real part constant. As the pole moves vertically, the frequency increases. But since the real part is the same, the exponential envelope is the same. This implies that the settling time will be the same for all waveforms. Also note that as the overshoot increases, the rise time decreases. If we now move the poles horizontally, that is changing the real part but keeping the imaginary part the same, we have figure B. Note that as the pole moves to the left, the response dumps quickly, but the frequency remains the same. Note that the peak time remains the same because the imaginary part is the same. And finally, if we move the poles along a constant radial line, we have figure C. Note that in this case, the percentage overshoot remains the same. Also notice that the responses looks exactly alike, except that the speed varies. The farther the poles are from the origin, the more rapid the response. Let us conclude this lecture with this example, which is found in page 184 of your textbook. Given the pole plot shown in this figure, we are to find the peak time, percentage overshoot, and the settling time from the pole locations. First, we need to find our zeta and our natural frequency omega subscript n. We have shown that the radial lines is omega subscript n. Therefore, we can easily find our omega subscript n using Pythagorean theorem, which is equals to the square root of 7 squared plus 3 squared. This gives us 7.616. We can then compute zeta as cos theta, which is 3 over 7.616. This gives us 0.394. We can clearly see that this is a case of underdamped system. From here, we will just apply the equations for the specifications to find the desired quantities. Therefore, the peak time is pi over omega subscript d, which gives us pi over 7. This gives us 0.449 seconds. And the percentage overshoot is given by this equation, e raised to the power minus zeta pi over the square root 1 minus zeta square, substituting the value of zeta into this equation and multiplying everything by 100, we get percentage overshoot of 26%. Try solving some other questions at the end of this chapter in your textbook so that you are able to familiarize yourself with solving problems with these equations.